Hello, Western. Now, I'd like to discuss another wave phenomenon that is related to the superposition principle. Now, recall that the superposition principle states that when two waves collide, the resulting disturbance is equal to the sum of the disturbances for the two waves. Now, I'd like to introduce just a bit of terminology. We say that when two waves add together to create a larger disturbance, we call this constructive interference. And when two waves add together and cancel out to create a smaller disturbance, this is called destructive interference. Now, when we discuss interference, it's very useful to introduce the concept of phase. Phase is basically just a way of measuring where the wave is in its oscillation. For example, is the wave at its maximum, at its minimum, at its equilibrium. Now, because we'll be studying interference and superposition, we'll be worrying mostly about the difference in the phase between two waves, and this is called a phase shift. So, in this example here, I have a figure of two waves, and the phase shift is just this distance here. A way of thinking about the phase shift is it's how far you would have to move one wave over so that the two waves lay on top of each other. Now, using this concept of a phase shift, we can write down a condition for constructive and destructive interference. So looking over here on the right, we can see that two waves will interfere constructively when the phase shift between the two waves is 0, or when the phase shift between the two waves is a wavelength, or when it's any integer times a wavelength. When the two waves add together constructively to form a larger disturbance, we say that these two waves are in phase. Now, thinking about destructive interference, if we look over here at this figure on the right, we can see that two waves will interfere destructively when the phase shift is half of a wavelength. In this case now, the maxima of one wave is at the minima of the other wave, and vice versa. So when we add these two waves together, the waves cancel out and we get no disturbance. This is called out of phase. So now I'd like to look at a simple example. This example says we have two speakers that emit a sound of 120 Hertz. The sounds leaving the speakers are in phase, and the sound travels at a speed of 340 meters per second. The speakers are facing each other and are separated by a distance of 5 meters. And we're asked to find all of the points between the two speakers where constructive interference occurs. So the first thing we should notice about this is that the condition for constructive interference is that the difference in the phase is equal to an integer times the wavelength. So clearly, I'm going to need to calculate the wavelength of this wave. And I wasn't given that, but I was given the frequency and velocity of the wave. So remember that the velocity of a wave is equal to frequency times wavelength. So using this, I can see that the wavelength of the wave is equal to velocity divided by frequency, which I guess in this case is going to be 2 meters. Now that I know the wavelength, I can start thinking about this condition for constructive and destructive interference. So let me erase this, and let me write this value that I have up here with the rest of my knowns. So what we have happening here is we have two speakers. So let me go ahead and draw a little figure of what's going on. So these two dots here are the two speakers, and they're separated by a distance of 5 meters. Now let's consider some point here, x. It's a distance x away from the speaker on the left. So if this point is a distance x from the speaker on the left, then it's going to be a distance 5 minus x from the speaker on the right. So we're told that the waves produced by the speakers are initially in phase. However, as the wave moves away from the source, its phase changes. So say, for example, here it's at equilibrium, now the wave's at a maximum, later it's at a minimum, and the phase difference between its source and this point x is just equal to x. And the phase difference between this point and this point x is 5 minus x. So the phase shift between these two waves is just equal to the difference in these two things. So the phase shift, or the difference in the phases, is equal to 5 minus x, or 5 meters minus 2x. And what we want to do is set this equal to an integer times the wavelength, which is 2 meters. So we said our condition for constructive interference was 5 meters minus 2x is equal to an integer times the wavelength. So solving for x, we see that x is equal to, or 2 times x is equal to 5 meters minus m times lambda. So x is equal to 5 meters minus m lambda over 2. And from here, we can just plug in different values of m. So if I plug in m equals 0, I have 5 minus 0 divided by 2, and we have that x is equal to 2.5. When m is equal to 1, we have x is equal to, now we have 5 minus 2 divided by 2, so we have 1.5 meters. And if m is equal to 2, we'll have x is equal to 0.5 meters. Now, notice that if I plug in m equals 3, I would have a negative number here, which means it's outside of the two speakers. So that's no longer in the area that we're considering. However, these aren't the only integers that we can consider. We could also consider numbers like minus 1. That's also an integer. So if we plug minus 1 into this, we would get that x is equal to 3.5 meters. And plugging in m equals minus 2, we get x is equal to 4.5 meters. So these are all of the locations where constructive interference occurs between the two speakers. And so I think that's where I'd like to end this video, and when we start up the next video, I'll start talking about this Young's double slit experiment.